trade-off for your application. All right, we haven't discussed boundary conditions. Now we are going to discuss boundary conditions. So a boundary condition starts from the finite difference approximation, and it particularly applies to the grid points near the boundary. So if we know U of L, if we know U of L and T equal to UL of T, and UL of T is given, it is provided, we don't need to solve for that. Then we know U1 of T is equal to this UL of T, right? U1 of T is the function value at the first grid point, and the first grid point is at the boundary. So we don't need to use any ODE to solve for that grid point. And then also du2 dt, which is approximated as u1 minus 2 times u2 plus u3 over delta x squared. This is exactly following our finite difference approximation. It's a little bit different from other ODEs because one of the numbers is given, right? So for all the other points, the time derivative depends on the neighboring 3 points. But for the point close to the boundary, it only depends on the solution at 2 neighboring points because the other one is given. So okay, now given this, we also have u of n minus 1 dt equal to u of n minus 2 minus 2un minus 1 plus u right. This is also given, delta x squared. Basically, the 2 points close to the boundary only depends on 2 points instead of 3. And given that, we can write the finite difference in matrix form. Okay, that is, if we can write our u, the vector of t, is equal to a vector. This is where linear algebra starts to come into play. u1 of t, oh, actually we don't have to solve for u1 of t, so u2 of t to start. Okay, u3 of t, etc. to un minus 1 of t. So this is my solution. It is a vector function of time. Then I want to write, okay, du dt equal to a times u. That's an awfully simple form of the finite difference discretization. So what is a? Oh, sorry, and the plus b. B is also a vector, right? So now what is a and what is b? So you know my vector is so my solution u is a vector of length n minus 2, right? So n is the total number of grid points minus 2 because I don't need to solve for the 2 boundaries. What is a like? What is the matrix A like? What is the size of, what is the shape? Yes?
Three-diagonal matrix with n minus 2 by n.
It's an n minus 2 by n minus 2 matrix, and you are saying it has 3 diagonals. That's exactly correct. Because the time derivative at every grid point only depends on the neighboring 3 grid points, except for the 2 boundaries, which only has 2 non-zero entries. Okay, so it turns out the matrix A, if you look at the boundary, if you look at the first, the du2 dt equal to ul minus 2 times u2 plus u3. So over delta x squared. So I know this one is minus 2 over delta x squared. This is the term that is going to contribute to the time derivative of u2 and gets multiplied also by the time derivative by the u2 itself. And then the second entry on the first line is 1 over delta x squared. It is multiplied with u3 and contributes to the time derivative of u2. And all the others are 0. Okay, starting from the second line, we have 3 non-zero entries. 1 over delta x squared minus 2 over delta x squared and 1 over delta x squared and 0 otherwise. And we have 1 over delta x squared starting from here, 0 here, and minus 2 over delta x squared here, and 1 over delta x squared here. So this diagonal, this tri-diagonal form continues to the last line, which has minus 2 over delta x squared and 1 over delta x squared here. Anything other than these 3 diagonals is 0. What is B? Why do we have a B? Boundary conditions, exactly. So that means starting from the second row, B is going to be 0, and B is only non-zero for the first entry and the last entry. That is compensate for the missing term here and the missing term here. What is this? What is the first entry? It's UL over delta x squared. The last entry is UR over delta x squared. All right. Okay, so now we have a ODE in this form. We know what A is, what B is. Okay, the rest of the task is basically solving that ODE, du dt equal to AU plus B. Okay, so how do we do this? So I'm going to review a little bit about like ODE solution methods. So we have talked about forward Euler, right? That is basically if you discretize u of n delta t is represented as u vector superscript n. Okay, so now you have discretized both space and time. You discretize the spatial component into a vector and the time component into a superscript. Then forward Euler means then I'm going to write down the ODE. du dt equal to AU plus B is discretized into u of n plus 1 minus un over delta t is equal to A times un plus B. And my B, remember, it depends on the boundary condition. It may also be time dependent. So I'm going to write B as also a function of n here. Okay? And if my B is specified as also in discretized form, maybe I need some interpolation. For example, MATLAB has an interp function for interpolation. Maybe I need some interpolation to go from the discretized form in the specified discretization into the discretization that matches my time step. Okay, so I have this, and I can, if I know what is un, I know I can calculate what is un plus 1. Okay, I can also have backward Euler. That is also discretizing the time derivative that way, but is equal to AU of n plus 1 plus B of n plus 1. And what is the advantage of backward Euler compared to forward Euler? Stability. So forward Euler is only stable for small delta t, and also requires the eigenvalues of the matrix A to be within a particular circle for a particular delta t. Okay, the larger the delta t is, the smaller the circle is going to shrink. And the backward Euler is basically stable for anything but a small circle. So it is much more stable than forward Euler. And for some systems, you may find for forward Euler, you're going to get infinity or not a number pretty soon. But with backward Euler, you may get stable solutions. Okay. But both forward Euler and backward Euler, they have a they have a disadvantage. What is that? Fixed time step? Not really, because you can have delta t to be different for different time steps. Huh? It's implicit? No, actually backward Euler is implicit. Forward Euler is explicit. For huh? Inversion of A? Yeah, for forward Euler you don't need to invert A. For backward Euler you do need to invert A, because this system has to be solved as identity over delta t minus A times un plus 1 is equal to un over delta t plus b of n plus 1, right? So you have, I mean, because un is known, un plus 1 is unknown. If you move the unknown to the left hand side, known to the right hand side, then you find you have a matrix system to solve. You need linear algebra for that, where for forward Euler you don't need linear algebra for that. Okay, that's the difference between explicit systems, which is forward Euler, and implicit methods, which is backward Euler. But still, nobody has answered my question. Both forward Euler and backward Euler has one common shortcoming. Yes?
First order accuracy.
Exactly, they are only first order accurate. Remember we discussed the order of accuracy in approximation of spatial derivatives. These ODE solution methods are also some kind of approximation for time derivatives. And there is also an order of accuracy with respect to time. Okay? So they are both first order accurate, which means the solution error you get, even though they are stable, shrinks only by a factor of 2 if you make delta t shrink by a factor of 2. And the ultimate solution, so in a PDE, let's remember, in a PDE, and this is a mistake that has been made by even some of my senior PhD students. So the solution error of a PDE has contributions both from spatial approximation and time approximation. Solution error is equal to O delta t to the power to the order of the time discretization plus O delta x to the order of the spatial discretization. All right. So if you choose a very high order spatial discretization and neglect to use a high order time discretization, you may be puzzled. Why do I get a bad solution? I have used the 8th order scheme in space. Why is my solution bad? Maybe you used only a first order time integration scheme, and vice versa. If you only have a first order scheme in space, maybe it doesn't make sense to use an 8th order time integration scheme. And okay, so these are only first order. There are methods I won't review here. Trapezoidal rule is second order. Runge-Kutta methods are even higher order. The MATLAB's ODE 45 function, I ask you to look at over here, switches between a 4th order scheme and a 5th order scheme. It actually does a 5th order time integration and uses a 4th order scheme to check the accuracy.